All right, let's talk about Erlang and OTP. We're going to dive into how this amazing telecom-grade technology gives us a masterclass in building software that's so reliable, it can pretty much heal itself. So let's just start with a question that kind of flips software design on its head. Most systems, they're built to avoid failure at all costs. But what if we just accepted it? What if we embraced failure as inevitable? And what if we design systems that don't just survive a crash, but recover from it instantly and automatically? So how do you do that? Well, the answer lies in the fundamental unit of work in any Erlang system. And it's not a thread, it's not a function, it's something way more powerful. And honestly, it's the secret to this entire philosophy. And that brings us to the Erlang process. Now, the first thing you have to understand is this is not like an OS process, not even close. Think of it less like some heavy-duty machine and more like a single, hyper-focused worker in a giant factory. It's got its own memory, it cleans up after itself, and, this is the most important part, it works in complete isolation. Nothing another worker does can mess with it. And when you put them side by side, the difference is just staggering. An OS process is heavyweight, it's expensive to create. An Erlang process, it's so cheap and light you can literally spin up millions of them on one machine. But the real game changer here is that isolation row. Because there's no shared memory, a crash in one process is completely contained. It can't start a chain reaction or corrupt its neighbors. And that right there, that's the bedrock of Erlang's fault tolerance. Okay, so we've got these millions of tiny isolated workers. Great, but how do you organize them? Well, this is where OTP, the Open Telecom Platform, comes in. It gives us the blueprint for building these systems that can actually truly heal themselves. And it all boils down to this one simple but really profound idea: let it crash. This is the absolute core of the Erlang philosophy. Instead of stuffing every single worker process with tons of complex error-handling code, you keep them simple. You let them fail, and you hand off the responsibility of recovery to a totally different type of process, the supervisor. And how does that work? Well, it's all managed by something called a supervision tree. Honestly, the best way to picture it is like a company's org chart. You've got the workers at the bottom doing all the real tasks, and then you have their managers, the supervisors. They don't do the work themselves. Their only job is to watch their workers. And if one of them fails for any reason, they just restart it. Simple as that. So let's watch this self-healing loop in action because it's so cool. First, bam, a worker process hits an error and crashes. Immediately, its supervisor gets notified. The supervisor doesn't panic, it just restarts the worker in a clean, fresh state. The fault is contained, the process is back online, and the rest of the system just keeps on trucking, completely unaware anything even happened. And this whole cycle can take just microseconds. So this supervision model is an incredibly powerful way to handle failures at runtime. But it kind of brings up another question, right? How should we actually write the code for these worker processes? Because without some kind of standard structure, we'd just be reinventing the wheel every single time we needed, say, a server. And this is where OTP behaviors come in. Think of them as battle-tested blueprints for common patterns. The most famous one is Gen Server, short for generic server. It basically gives you a complete, super robust server implementation right out of the box. It handles all the tricky, low-level stuff for you. And this is the result, a way cleaner system. I mean, look at the left side. You've got this tangled mess of business logic and server plumbing all mixed together. But on the right, with Gen Server, you get this beautiful, clean separation. OTP handles all the generic hard parts, the message loop, state management, all that stuff. And you, the developer, you just provide a callback module with your specific business logic. You get to focus on what your app does, not all the plumbing that makes it work. And finally, we bundle everything up. We take our supervised processes, our behavior modules, and we package them all into an OTP application. It's a self-contained component with its own supervision tree that you can start, stop, and manage as a single cohesive unit. This is really the highest level of organization you'll see in an Erlang system. Okay, so let's take a step back and recap how all these pieces fit together to build these incredibly resilient systems. So here they are, the 4 pillars of OTP reliability. But the crucial point, the thing you have to get, is how they all work together. It's not just one thing. Lightweight processes give you isolation. Message passing keeps communication safe. Supervisors give you that automatic recovery. And behaviors give your code a solid, proven structure. It's the combination of all 4 that makes this such a powerful philosophy. And when you really think about it, the OTP approach isn't about trying to write bug-free code. I mean, that's impossible, right? It's about engineering a system that accepts that failures will happen and is built from the ground up to handle them gracefully and automatically. And that is the core takeaway here. Erlang and OTP prove that the most resilient systems don't just try to avoid failure, they are built to master it. By embracing failure as just a normal part of a system's life, you can build applications with a level of uptime that honestly feels like magic. It's a powerful engineering philosophy that continues to power some of the most dependable systems in the world today.